about minimal thermodynamic cost of computing with circuits. This is a project I've been working on with David and Abhishek. So in computational complexity theory, we classify how difficult it is to compute a function based on a resource cost. So such as like the number of steps it takes to compute it, so like time complexity, or the memory, so space complexity. But no one had so far have considered the energetic cost as a measure of complexity. So we attempt to do that in our work. So what's coming is I'm gonna introduce what a Boolean circuit is and a little bit about circuit complexity theory, and then I'm gonna talk a little bit about mismatch cost and then show some results. Okay. So what is a Boolean circuit? Boolean circuit is just a collection of logical gates, those are like and or not, that compute a Boolean function for a specific input size. So the way we represent it is by directed acyclical graph. So the edges would be the connection between the gates and the vertices would be the gates. So this is an example here of a Boolean circuit. And there is two main measures in circuit complexity theory to measure like complexity of a circuit. It's size and depth. So size is the number of gates in the circuit, and depth is the longest path from an input node to an output to the output. And the way we run the circuit, since it's not entirely clear just looking by at the graph, is basically we use a topological ordering. So we start by writing the inputs, then updating the first gate, then updating the second gate, and so on until we are done. And when we rerun the circuit, we run the circuits multiple times. So we don't initialize the gates. We leave the gates we use the results from the last run, and then we start by reinitializing the inputs and so on, making a breaking correlation as we go. So as I was saying, at the end of each run, the inputs and the gates are correlated. As we are writing the new inputs, the inputs and the gates are no longer correlated, and as we update the circuit, we make and break correlations. And just a little bit of mismatch cost. I can't go into details because of time, but basically mismatch cost is the extra thermodynamic cost incurred when a physical system is running an input distribution that does not match the input distribution that was optimized for. So just a quick explanation. If we have a process that takes an input distribution P0 to P1 and a cost function C, we can just using simple algebra rewrite the cost function, adding and subtracting CQ, where Q is the distributions that minimize the cost. And if we rearrange the terms, this term, which equals the drop in the KL divergence, is the mismatch cost. And so if we apply that and we measure the mismatch cost of the reinitializing inputs, I spare you the algebra for time, but we will get that cost would be the mutual information between the inputs and non-inputs plus KL divergence between the input distribution and the prior. And similarly, if the associated mismatch cost of running each gate, we would get that it is equal to the mutual information between the gate and its children plus the KL divergence between the joint distribution of the gates and its parents versus the prior minus the KL divergence of probability distribution of the parents minus the prior. Here, so if this is the way, we can see that we plot that equation for a few types of gates like AND and OR and XOR. We have IID inputs, and here we vary the prior of the gate. So on the x-axis, we have the probabilities that the gate, the probability that the gate in state 1 is on the x-axis. So as we see here, for example, for an AND gate, the cost would be extremely high as the probability of the state 1 is higher, because an AND gate usually have 3 states that are 0 and 1 state that's 1, versus, for example, an OR here we'd see it's highest when the probability distribution is closer to 0. So here we have a circuit that we ran multiple experiments on. It's we call it the tree of AND gates. Basically, we have a number of inputs and then an AND gate to each 2 inputs, and then an AND gate to each 2 AND gates, and so on. You can imagine extending this for even higher depth. So we'd have like 4 AND gates, then 2s and 1, and so on. So it's kind of similar to a binary tree, so we call it a binary tree of AND gates. And here we plot the total cost of the running this circuit, and for both implementation, but for gate by gate and layer by layer implementation. So for the blue line, we would just run the first gate, then the second gate, and the third gate. For the orange line, we would run this first layer, so we would run those two gates simultaneously. So it's a coarse graining in time, and we would see that the cost is actually lower as we expect. And here we will show this in the way. Right. Here we would show a theorem we have proved about the upper bound of the mismatch cost. So we would see that the upper bound of the mismatch cost of running one gate is always upper bounded by the logarithm of 1 over the smallest probability in its prior. And if we assume that all the gates have the same prior, we would see that the mismatch cost of the running the entire circuit is upper bounded by the number of gates in the circuit times the logarithm. Here, this number of gates with the circuit is the size complexity, so we would see how mismatch cost would relate to size complexity in this case. So here we ran an AND binary tree similar to the one we saw before, but we changed one gate in each layer to be an OR. And we ran two scenarios where the OR had a similar uniform prior as the ANDs in the tree, and where this one OR had a different prior, which is heavily opposed to OR, so like heavily skewed towards one. And we would see that even the scaling in the first one is linear, as we expect. The second one is not actually, at least in the small circuit scheme. And yeah, and this cost is higher as well. So finally, we can ask just a simple question is, does the circuit with the minimal mismatch cost always correspond to the circuit with the minimal size? And the answer is no. A very simple, small example would be an AND gate. So, and if I want a circuit that implement an AND, the smallest circuit would be an AND gate, but choosing the prior correctly, we can get much lower mismatch cost by using an OR and a NOT instead. So yeah, that's pretty much it. And yeah, thank you all.
Okay.